I'd like to summarize briefly what we've talked about in terms of different kinds of matrices, and then go on to talk about the input-output model. So we've talked about Markov matrices and positive matrices, and a little bit about non-negative matrices. And in all of these cases, there is a real eigenvalue. That's one of the important things about them. And remember, a Markov matrix is one in which the sum of the columns is equal to 1. And all of the entries are non-negative, so between 0 and 1. Positive matrix is simply a matrix where all of the entries are positive. And a non-negative matrix is, of course, one where all of the entries are greater than or equal to 0. Okay, now, besides the property of having a real eigenvalue, there are various other special properties that these matrices have. So let's look at those. Well, here's some properties that they all have. So as I mentioned, they have at least one real eigenvalue. Typically, they have more than one. And if you take lambda max to be the biggest eigenvalue, and that is to say the one with the biggest absolute value, then that's the one that's real. Lambda max is real. And since it's maximal, I'll just emphasize that what that means is that the absolute value of lambda max is bigger than the absolute value of all of the other lambdas. And another property is that the lambda max eigenvector is positive. It has all positive entries. Now, it could have all negative entries too if you multiplied it by -1, but you can take it to have all positive entries. And those properties, as I said, hold for all of these types. Now, furthermore, in the case of a Markov matrix, this lambda max is 1. That's an important thing. That's this steady state business about Markov processes. And the eigenvector, the eigenspace is one-dimensional. Positive matrices are similar. Well, lambda max doesn't have to be 1, but again, it has multiplicity 1. There's a one-dimensional lambda eigenspace. And non-negative, well, non-negative you can take to be a limit of positive ones. And so you conclude that the maximal eigenvalue must be greater than or equal to 0. But it turns out it's not necessarily multiplicity 1. And I realized when I said all positive entries up here, I should have said non-negative in the case of a non-negative matrix. Okay, I want to go on now and look at the input-output model. This is due to Leontief. And let me illustrate it with an example. So we have two types of goods. We have power and we have steel. We're interested, we have a power plant and a steel factory. And in order to produce 1 unit of power, well, you need to run the factory. So you need 0.5 units of power. And you also, let's say, you need some steel. And in order to produce 1 unit of steel, well, you don't need any steel to go into it, but you do need, let's say, 0.2 units of power. Okay, so what that means is, suppose I have X units of power and Y units of steel. Well, in producing that, we're going to use up 0.5x plus 0.3y units of power, and similarly for the steel. So let's put this in a matrix, 0.5, 0.3, 0.2, 0, like this. What this equation says is if we're producing x units of power and y units of steel, we're going to consume 0.5x plus 0.3y units of power and 0.2x units of steel. Okay, now let's say we have a target level of production, which is to say D1 and D2. We'd like to, in addition to the amount that we use up, we'd like to have this left over. and that we can sell on the market or whatever. So the equation that we have is this amount of production plus the amount of production that we're going to take to market is supposed to be the total production, which was X and Y. So we wind up with this equation. If this is A, we're trying to solve AV plus D is equal to V, where D and A are given, and we're trying to find V. So that's just this equation. So I'll just write that as I minus A times V is equal to D. That's the equation we'd like to solve. Well, that doesn't look too hard. We just need to know that I minus A is invertible. But now here's the crucial point. We really want this inverse, I minus A inverse, to be non-negative. This has some meaning because the solution is going to be I minus A inverse times D, and D is some positive numbers. And I'd like this to have meaning, and so I'd like this to be positive for any choice of D. So this I minus A inverse had better be a positive matrix. Well, if you have a real eigenvalue which is bigger than 1, then you lose, because I minus A is going to have an eigenvalue 1 minus lambda, and that's certainly going to violate this. So the key point is that if lambda's minus 1, then everything works. That's the sort of punchline of the input-output model. The fact is that if lambda is less than 1, actually all of the eigenvalues are less than 1 in absolute value, then I minus A inverse is a non-negative matrix. And this is kind of cool why this holds, so let's look at that. So it's a very clever trick to see this. So I'm going to remind everybody about an identity from one variable. 1 over 1 minus x has this power series expansion. And this is an infinite series. And the way you know this is true is you multiply both sides by 1 minus x to bring the 1 minus x to the other side. And then I'm claiming that 1 is equal to 1 minus x times this infinite power series. And now you just multiply it out term by term. You get 1, and let's see, the next term is minus x, and then after that you get a plus x, and then a minus x squared and a plus x squared, and they all cancel pairwise. And everything except for the leading term cancels, and you get 1. So that's why this is true. Now, of course, this only makes sense if this converges, which holds if the absolute value of x is less than 1. Well, the same thing holds for matrices. You just have the following identity. I minus A inverse is this infinite sum. And the proof of that fact is exactly the same. You cancel terms term by term. And of course, you need to know that this infinite series converges. And the fact is it does if the eigenvalues are less than 1. And if that's the case, then you conclude that this inverse is this infinite sum of a bunch of matrices, all of which have positive entries, or I should say non-negative entries. So you're just adding up a bunch of matrices with non-negative entries, so I minus A inverse is non-negative. Pretty clever, huh? So let's just look at our example. There's our matrix, and it turns out that I minus A inverse is rounding off this matrix, which has all positive entries. And so if you had any starting value D, you could multiply it by this, and you get something with positive values, which would be meaningful. So that's the input-output model.